SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 24 and we are going to continue with our discussion on bending of beams. Okay. So, in the last class we did what is called pure bending of beams, in which case the moment was constant along the beam. So, that is uniform bending of beams, whereas in this class we will do what is called non-uniform bending of beams. Okay. So, as the name suggests, in this case the bending is not constant along the length of the beam, and you can recall from the last class that the bending moment m of x was equal to E I times the curvature, bending curvature, right. So, if bending moment is not constant, then the bending curvature is also not constant along the length of the beam. So, let us see what extra complications arise when there is non-uniform bending. All right. So, let us again have a look at the beam. So, here is the beam. Think of a general case when we have distributed load also acting along the length of the beam. So, in the uniform bending case there was no distributed load or there was no transverse load also. Okay. And let us call it B of x, and here is my x axis, then we have the y axis, and coming out of the paper is the z axis. Okay. So, the distributed load is acting in the positive y direction. Now, let us cut a small section of this beam which are at a distance x and x plus delta x. Okay. So, we are thinking of this section and draw its free body diagram. Here is that section and the length of the section is delta x, and we have B of x as a distributed load on this small section, and then at the two ends of this section we have bending moment m of x plus delta x, because you see the right cross section is at x plus delta x. So, bending moment has to be evaluated at x plus delta x, okay, whereas on the left cross section the bending moment is m of x. All right. Then we also have shear force in this case, you see, because we have distributed load also acting here. So, in the cross section not only we have bending moment, we will also have shear force. Now, by convention on positive cross section, that means on cross section having normal in the positive x direction, shear force in the positive y direction will be counted as positive, whereas on the negative cross section shear force acting in the negative y direction will be positive. Okay. So, we have on the right cross section, which is the positive cross section, shear force is plus upward. So, it is V of x plus delta x, whereas in the left cross section shear force goes downward and it is V of x. Okay. Now, let us do the moment balance of this small section about the center of the left cross section. Okay. Let us do it about this point, let us call it O. So, moment about O, since it is in statics, that should be equal to 0, right. So, net moment about O has to be equal to 0. So, we will have m of x plus delta x which is along z direction. So, it comes with positive E3, then m of x, you see it is clockwise. So, it is in the negative z direction. So, it comes with minus m of x E3, right. Then we will have moment due to V of x plus delta x, and that is simply equal to plus delta x into V of x plus delta x, and that is also along E3. How about moment due to V of x? So, you see V of x is passing through the point O, therefore, it does not generate any moment. And finally, we also will have moment due to the distributed load, right. So, that is going to be an integration plus the moment due to distributed load. So, that is from x to x plus delta x, and then the moment would be the arm which is zeta minus x into b of zeta d zeta. So, you see zeta minus x is the arm of the force from the point O. Okay. Let us say this point is zeta. So, this distance, that is your zeta minus x, okay. And this is also in plus E3 direction, and this has to be equal to 0, right. Now, everything is pointing in the E3 direction. So, we simply extract the E3 component of this equation, and that tells us that m of x plus delta x minus m of x plus delta x into V of x plus delta x plus this integration of x to x plus delta x times zeta minus x b zeta d zeta, that has to be equal to 0, right. And since this holds for any arbitrary section of the beam, we can divide this by the length of that section, which is delta x. So, let us divide it by delta x, and further take the limit as delta x goes to 0. Okay. So, what do we get? Can you see that the first two terms simply is the derivative of the moment. So, that is dm by dx. Then the next term is simply V of x, and what about the last term? So, last term actually is going to vanish, is not it? Why is it so? Because you see the length of the integration, that is x to x plus delta x. So, the length is delta x itself, and when you divide by delta x, then what you get in the limit is simply the integrand. Okay. So, you have to take the limit delta x going to 0 and then the integrand zeta minus x b zeta. Now, you see what happens to zeta minus x. So, as delta x goes to 0, the arm, that is also going to 0. So, this is than 0. Okay. So, we have finally derived a relationship between the variation of bending moment and the shear force V of x. Okay. This is that dm by dx is equal to minus V of x. Okay. So, it is a very important equation that we have derived and we are going to use it later on. So, basically it says if moment is varying in the beam, then there has to be non-zero shear force V of x. If V of x is 0, that means if shear force is 0 all along the beam, then the moment would be constant, but if there is shear force in the beam, then moment will start to vary. So, we are doing here non-uniform bending, which means there is non-uniform bending moment. So, there has to be shear force also in the beam. Okay. All right. Now, once there is shear force in the beam's cross section, then what can we say about the different traction components that would be present in the beam's cross section? So, let us have a look at the beam's cross section. So, we have rectangular beam, let us say, and this is the x plane, right, cross section has normal along x. So, we have sigma x x here as the normal component of traction, and this arises due to bending of beams. Can you recall that this was equal to minus of bending moment m at the cross section x times y, where y is the distance from the neutral axis, divided by I z z, is not it? So, this is something that we derived in the last class. So, this is the bending stress, the normal stress sigma x x, it is also sometimes called bending stress. Okay. But will this all be there, or there will be some more traction components? The other traction components are tau of x y and tau of x z. Now, see, in this case we have shear force also in the beam, and that is along the y direction. So, the V of x, the shear force is in the y direction. If tau x y is 0 in the cross section, what is tau x y? This is the component of traction in the y direction, right. You see, we have used the symmetry that tau x y is equal to tau y x. So, we are talking about traction components on the x plane and then in the y direction. So, that is tau x y. If it was not symmetric, then we would call it tau y x. Anyway, so tau x y, then this also cannot be equal to 0. If it is equal to 0, and when you integrate this in the cross section, this will also give you 0, but then we have a non-zero shear force V of x. Okay. So, therefore, this is not equal to 0, and tau x z, we can say that it is equal to 0, there is no shear force in the z direction. So, locally also tau x z would be close to 0 in this case. Now, the question is how tau x y is varying in the cross section. So, that is the question, how the shear component of traction which is tau y x, but that is also equal to tau x y, varies in the cross section. All right. So, we are again going to make an assumption while deriving the variation of shear component of traction, which is that tau x y is only a function of y, it is not a function of z. Okay. So, let us again have a look at the cross section. So, here is the cross section. and suppose this is your neutral axis. So, we have y axis and z axis which coincides with the neutral axis, and any point in the cross section is y comma z, and we are saying that shear component of traction does not depend on z. So, this means tau x y, which should ideally be the function of both y and z. We are saying that this is only a function of y. So, it is constant along the z line. So, if we try to draw the distribution, then we have something like this. The shear traction has got uniform magnitude, therefore, these arrows have the same length. If you take a different y line, so if I take a different line, let us say a line over here, then the shear traction there would be something else. Maybe it is larger, we do not know, which we have to find out. Okay. So, to find this distribution of shear traction, we will have to cut out a section, a small piece from the beam. So, let us draw a 3D diagram of the rectangular beam first. So, we have a rectangular beam, and it is clamped on one end, and then we have the neutral plane which passes through the centroid of the cross section. So, this is my neutral plane. Okay. And think of a small piece here, this green piece that we are going to carve out. Okay. So, let us take this green piece outside, and suppose that the bottom plane of this green piece and the neutral plane, they make a distance of y between them. Okay. So, this distance that is y. So, the bottom plane is at a distance y above the neutral plane. All right. So, let us take out this green piece and draw all the forces that acts on this green piece. Okay. Now, see it has got so many faces. The top face, that is the positive y plane, right. So, on that face what is going to act? It is the distributed load B, can you recall? So, this is the plus y plane and we have got B of x acting here. Okay. The bottom plane, what can you say about the bottom plane, which is the negative y plane? So, on the negative y plane, what would be acting there? So, we will have tau x y, is not it? Tau x y, since it is a negative y plane. So, tau x y will be pointing in the negative x direction. So, it goes backward, right, and it is all along the negative y plane. It is also here, it is also here. Okay. It is all along the bottom negative y plane. What else is there? There could be sigma y y, there could also be tau z y, right. What other phase is present here? Look at the positive z phase and negative z phase. You see the positive z phase and negative z phase, they are the outer lateral surface of the entire beam, and we are assuming that we have distributed load acting only on the positive y plane. So, the positive z plane and negative z plane of this whole beam is actually traction free. Okay. So, we have nothing. So, positive z plane and negative z plane, we have 0 traction. All right. Now, what remains is the positive x and negative x plane. So, what do we have on the positive x and negative x plane? So, positive x plane, for example, we are going to have sigma x x, the bending stress, then tau y x, which we are saying is same as tau x y, and similarly we have tau z x, which is also equal to tau x z, right. So, we can draw these components on the positive x plane. So, they are something like this. Which is sigma x x, but at x plus delta x, right. And we also have tau x y, and since it is a plus x plane, tau x y is going to act in the plus y direction. So, we have tau x y also. Okay. Similarly, we can also draw the traction components on the negative x plane, but let us not do it because it is going to make things messy. Now, let us do the total force balance only for the force in the x direction. Okay. So, let us do the force balance in the x direction. Okay. So, we have positive x plane and negative x plane on which we have sigma x x. So, we have an integration over the x plane. So, this is the x plane, and we have sigma x x at x plus delta x comma let us say eta comma gamma. So, any point in the cross section has got y and z, y is eta and z is gamma, right, and then d eta d gamma. And you see here, suppose eta is the y component. So, eta is going to vary from y to h by 2 if h is the height of the cross section. So, if we say that this is h and this is b, then eta goes from y to h by 2, is not it? The bottom face of the green piece is at y and at the top face it is h by 2. So, here we can say that eta is in this range y comma h by 2, and what about gamma? Gamma would be in the range of minus b by 2 to b by 2, is not it? If the total width is b, then it goes from minus b by 2 to b by 2. Okay. Similarly, we also have force on the negative x plane, right, and then the positive z and negative z, they are traction free. So, we look for the force on the positive y and negative y plane, all right. So, when we add the total force, so add the total force so for the x and negative x plane, we will have sigma x x of x plus delta x comma eta comma gamma minus sigma x x, but at x only comma eta comma gamma into d eta d gamma. So, that is the contribution due to x plane, and then the contribution due to y plane. So, we have two y planes, y plane here, and in the x direction the force that is acting is tau x y, but you see it was in the negative x direction, because on the bottom face the shear traction is in the negative x direction. So, it comes with a minus sign, minus tau x y into d zeta d gamma. And where does zeta and gamma vary? So, zeta, for example, the x coordinate, it varies from x to x plus delta x, right. So, for this one, zeta is an element of x to x plus delta x. And what about gamma? So, gamma is the z coordinate, right. So, look at the picture here, the gamma goes from minus b by 2 to b by 2, is not it, the z coordinate. Okay, let us now plug in the formula for sigma x x. So, we know that sigma x x is actually minus m x into y coordinate divided by I z z, is not it? But here the y coordinate is eta. Okay. So, this is nothing but eta. So, we are going to plug that in here. So, we get integration over the x plane, and you see the x plane is just a small part of the cross section, it is not the entire cross section. The x plane in the y direction varies from y to h by 2, it does not vary from minus h by 2 to h by 2, because we are only looking at the x plane of that green element, Okay. Can you look back here? So, the x plane only of this green element here. All right. So, let us go back to our derivation. So, sigma x x becomes minus m z, the moment along the z axis, at x plus delta x. Recall that the moment is a cross section property, it only varies along the length of the beam, into the y coordinate, which is eta here, divided by I z z, and then we have another minus sign. So, minus m z, but at x only, into the y coordinate, which is again eta, divided by I z z, and this I z z, the second moment of area of the cross section about the z axis, that could also be varying along the length of the beam. Suppose that your cross section, the rectangular cross section, the dimension, width b and the height h, they are varying along the axis. So, in that case your I z z, which is 1 over 12 b h cube, that is also going to vary along the length of the beam. So, this could also be a function of x. Okay. So, we have this thing multiplied with the area dA of the x plane, right, and then plus over the y plane. So, we only take the bottom y plane, the top y plane where distributed load is acting. We are saying that distributed load is only in the vertical direction, which could be either upward or downward, but there is no distributed load in the horizontal direction along the x axis of the beam. So, we do not get any contribution from the top y plane, the positive y plane. So, this is only the negative y plane. Okay. So, we have minus tau x y, and you see what does tau x y depend on. So, tau x y in general, it is a stress component, it varies in the body. So, it is going to be a function of all the 3 components of the point, is not it, which in this case is zeta for the x component and y for the y component. See, the y should not be replaced with eta here, because we are talking about the negative y plane, the bottom face of the green element, where the y coordinate is y itself. Okay. So, it is y comma gamma, right, into d zeta d gamma. All right. So, let us further proceed, and you notice now the first integration, which is over the x plane. So, for each of the x plane, positive x plane or the negative x plane, the x coordinate is not changing, x coordinate is fixed, because it is a cross section, right, it is a part of the cross section. So, that means m z I z z, we can take it out of the integral, is not it. So, we have minus of m z at x plus delta x minus m z at x, okay, divided by I z z. Let us take a simpler case where I z z is constant, okay, and then integration over the x plane of eta dA, okay, minus tau x y of zeta comma y comma gamma d zeta d gamma, and this is negative y plane, and this has to be equal to 0, because this is the total force in the x direction on that green element, and it has to be equal to 0. and you see the green element that we took in the beginning, its length along the axis of the beam is delta x, which can be arbitrary. So, you can choose the green element such that the length could be as small as possible, right. So, this means in our final derivation we can simply divide by delta x also and then take the limit as delta x goes to 0, okay, because this holds for any delta x. So, we divide by delta x and let us take the limit delta x going to 0. So, that we are compressing that green element as small as possible, all right. So, let us see what we get finally. So, we can see that the thing here outside the integral we have minus m z x plus delta x minus m z of x divided by delta x, right, and we apply the limit here delta x going to 0 into 1 over I z z times integral over x plane eta dA minus, now you see tau x y, which we are saying right now is a function of zeta y as well as gamma, and gamma is the z coordinate, and we said in the beginning that let us take an approximation such that tau x y does not vary along the z coordinate. So, that means tau x y is only a function of zeta and y now, okay. It is not a function of gamma. So, in that case we can work out the gamma integral, because tau x y is going to act as a constant, and when you do the gamma integral you simply get the width of the cross section, right. So, we now have integration only along the x coordinate, which goes from x to x plus delta x, and we have the width outside b, and we have tau x y of zeta comma y d zeta, right, and then we have to also divide by delta x here. So, divide by delta x and take the limit delta x going to 0, is not it, and what you get here. So, in the limit delta x going to 0, the range of the integration is shrinking. So, we simply get tau x y into the length of the integration interval, which is delta x, divide by delta x. So, we just get tau x y, right. So, finally, we get a very simple formula that minus d m z by d x into 1 over I z z into integral over x plane eta dA minus b times tau x y of x comma y, that is equal to 0. Okay. And now dmz by dx, we know it is minus of v of x, right. So, this thing here, that is minus of v of x. So, when we work out the whole thing, we have v of x divided by I z z into the integral over x plane of eta dA minus b into tau x y of x comma y is equal to 0, all right. Now, let us look at this integral here. See, this integration is for the x plane of that green element, whose y extent is from y to h by 2. So, basically we have this cross section and then we have the neutral axis here, and we are at a distance y above. Okay. So, the x plane that we have here is this shaded area. And the integration here, which is eta dA, is nothing but the y moment of the shaded area, is not it? So, this is y moment of the shaded area, right, because it is integral of eta dA, where eta is the y coordinate. So, first moment in the y direction, which we will denote by q, okay, and it is a function of y, because you see the shaded area, it starts from y and goes up to h by 2. So, as you change your y, the shaded area is going to change, and likewise the first moment of the shaded area is also going to change, is not it? All right. So, finally, we have the formula that we wanted, that tau x y of x comma y is then v of x into q of y divided by I z z into b, okay, v q by I b, where b is the width. In case the width is changing for different y. So, suppose that we have a cross section which is very common in the strength of materials, and we call it I section. Okay. So, suppose we had an I beam whose cross section looks like an I. So, its centroid would be at the center of this I beam because it is symmetric. So, the neutral axis also passes through the center, and we measure y from the neutral axis. So, if this is your y, then your width is just this b, and if this is your y, then this is your entire width. So, b can also be function of y. Okay. So, we can say that this b here is also a function of y. So, with this formula we have finally derived how does the shear stress vary in the cross section. You see, in the formula moment is not appearing, sigma x x, the bending stress was minus m y by I z z. So, it was proportional to moment, whereas the shear stress is proportional to the shear force V x, which is minus of dm by dx. So, shear stress depends on how is the moment changing along the length. All right, let us try to see how does this distribution look like for a rectangular cross section beam. So, if we have a rectangular cross section, and here is neutral axis, and I am at a distance y, and I want to know what is tau x y on this line. You see, tau x y will be same everywhere on this line, right, because it is not a function of z coordinate, it is only a function of y. So, when we want to know tau x y at a point whose y coordinate is y, then we draw this y equal to constant line and look at the shaded portion above that line, and find out the first moment of this shaded area q, and then apply this formula, is not it. So, let us see what do we get in this case. So, here of course, the width b is constant, it does not change with y. So, B y is equal to B, and I z z. So, I z z we had already derived, it is equal to 1 over 12 B h cube, right. So, what will be q of y? So, what is the q for this shaded area? So, since it is the first moment, it would simply be y coordinate of the centroid of this shaded area times the area itself. Now, where is the centroid of this shaded area? So, you see this shaded area would be having its centroid somewhere in the middle. So, what is this distance? First of all, this distance, that is h by 2 minus y, correct. So, this distance is then simply half of it. So, this is h by 4 minus y by 2, right. So, therefore, this distance would be y plus this distance h by 4 minus y by 2. So, it is y plus h by 4 minus y by 2, which is half of y plus h by 2. Okay. So, that is your y bar, the y centroid of the shaded area. What about the area itself? So, the area A is simply base into height, because it is a rectangular shaded area. So, that is B times the height, which is h by 2 minus y, right. So, what is q y then? So, that is half of B into h by 2 minus y into h by 2 plus y, and this becomes half of B into h square by 4 minus y square. So, that is your q of y. So, finally, your tau x y, so tau x y is then shear force V of x into q y, which is 1 over 2 times B into h square by 4 minus y square, divided by I z z, which is 1 over 12 B h cube into B itself, right. So, we get several cancellations here. So, this B cancels with this B, okay. And finally, we see that tau x y is equal to V by B h into 6 times h square by 4 minus y square divided by h square. Okay. So, we have done some clubbing of the terms, and I will tell you why we did it like this. So, this implies that tau x y is finally V by B h into 6 into 1 by 4 minus y over h whole square. Now, can you see what is this distribution going to look like? See, what is V by h? V is the total shear force and B h is the total area of the entire cross section. So, V by B h gives me average shear stress, is not it? So, this part is your average shear stress. So, therefore, we clubbed it in this way, and then we have the remaining part 6 times 1 over 4 minus y by h whole square. Let us try to see this distribution. So, suppose this is the y line. So, this is y line and here we have tau x y. So, y line goes from minus h by 2 to h by 2, right. Now, you plug in y equal to h by 2, what do you get? You simply get tau x y equal to 1 by 4 minus 1 by 2 whole square, which is 0. So, at y equal to h by 2 as well as at y equal to minus h by 2, this formula tells me that tau x y is 0. So, it is 0, whereas at y equal to 0, this tells me that tau x y at y equal to 0 is tau average into 6 by 4, which is 3 by 2. So, it is 1.5 times the average. So, it is somewhere over here, and then in between it has to vary quadratically. So, you simply draw a curve and that becomes your formula for tau x y. So, this is tau x y equal to 3 by 2 times tau average into 1 by 4 minus y square by h square. All right. Okay. So, interesting result, is not it? Although we have some shear force in the cross section, the shear stress is not constant. It is varying quadratically in the rectangular cross section and its maximum value is at the centroid when y is equal to 0, and then it vanishes at the two ends at y equal to plus minus h by 2. Can we make a guess why did it vanish at the two ends? Why did tau x y vanish at y equal to plus minus h by 2? So, let us again have a look at our entire beam. So, y equal to plus minus h by 2 are the two sides of this cross section, right, the top side and the bottom side. So, this one is y equal to h by 2, whereas the bottom one is y equal to minus h by 2. But you see these sides also belong to the top surface and the bottom surface, which are your y planes. Now, we said that the distributed load when it is acting is only vertically upward or downward, it has no x component. So, that means on the positive y plane tau x y, the component of the traction in the x direction tau x y should be 0, because we are not applying anything in the x direction, right. And therefore, on the cross sectional plane also, when we were finding out tau x y, then at y equal to h by 2, which is also the part of the top plane of the beam, the shear traction vanished. So, you can now see the connection, right, why it vanished at both y equal to plus h by 2 and minus h by 2. See, in this entire derivation we used an approximation that tau x y does not vary when z coordinate is changing, is not it? Now, think of a circular cross section. Suppose we have a beam having circular cross section. So, here is the centroid. So, we have the y axis and then the z axis, and think of a line with y equal to constant. So, as per our approximation tau x y should be constant all along this line, right. So, it will have a constant value, and even at the ends here it should have the same value as it is at z equal to 0 all along, but it is conflicting. See, this is your circular beam. So, think of this circular beam, and suppose we are applying distributed load on the lateral surface. So, let us now think of also using the cylindrical coordinate system. Things will be easier visualizing when we use cylindrical coordinate system. So, this lateral surface is the radial plane, is not it? And on the radial plane we have the applied load which is perpendicular to the axis of the beam, right. So, these loads are perpendicular to beam's axis. So, what can we say about the various traction components on the lateral surface? Since it is a radial plane and the loads are perpendicular to the axis, and in cylindrical coordinate system your axis is z. So, this tells us that tau z r should be 0 on lateral surface, right. But then by symmetry tau r z is also equal to 0, and what is tau r z? This is the radial component of traction in the z plane. So, this is radial component of traction on z plane. So, this tells me that all along the periphery of the cross section, which are also the part of the lateral surface of the beam, tau r z should be 0. So, here on the cross section's periphery, tau r z is equal to 0. So, you see the shear has got no radial component, it can only have the theta component. But have a look at this distribution. As per this distribution, the shear tractions are all vertical. So, even at the ends the shear traction will be vertical. So, it will have both radial as well as theta component, right, because the vertical direction you can resolve it along the radial as well as theta direction, and you get non-zero components along both radial and theta direction. So, this is contradictory because we just saw that tau r z should be 0, but this distribution does not give me tau r z 0 on the periphery of the cross section. So, this tells us that for the circular cross section our assumption that the shear traction should be constant as you change your z coordinate. So, that is not a good approximation. Okay. So, we should avoid using this approximation for circular cross section, but still with this assumption of shear traction being independent of z coordinate, it still gives you some approximate result. So, people also use this formula even for circular cross section. All right. Now, finally, let us see how will the distribution look like for I beam. So, if we have this I beam, So, here is the neutral axis, and we are at any distance y from the neutral axis. Then what is tau x y here? You simply use this formula, it is equal to V x into q y divided by I z z into the width b of y. But you see, in this case width b changes abruptly, is not it? So, once you go from this length to any length higher than this, b changes abruptly. So, this means when you draw your profile, so supposing that this is your y and this is your tau x y, then it is again going to start from 0 and it would vary quadratically, and after this there will be a finite jump, because you see the width b decreases, therefore, the shear stress will increase and there will be a finite jump, and then again it is going to vary quadratically, and then it is going to be symmetric about this line. Okay. There is again a jump and then symmetric. So, in this case we have jump in tau x y, all right. So, that is about non-uniform bending of beams, and in the next class we will talk about bending of asymmetric beams, the cross sections which are not symmetric. So, here we talked about rectangular cross section, circular cross section or I beams. All these cross sections are such that they are symmetric about the y axis, is not it? But what if the cross section has no symmetry, if it is an arbitrary cross section, then how does bending happen for beams with such cross sections? So, that is the topic for the next lecture. Okay. Thank you.